At University booth at Design Automation Conference 2013, we demonstrate our work on charge management optimization of the hybrid energy storage systems. This work is a part of research collaboration between Professor Naok Chang's group at Seoul National University and Professor Masood Pedram's group at University of Southern California. A hybrid energy storage system is composed of multiple heterogeneous energy storage elements such as batteries and supercapacitors. Last year at the university booth, we demonstrated a working prototype of the hybrid energy storage system composed of supercapacitor, lithium-ion batteries, and lead-acid batteries. This year, we demonstrate automated optimal control of the hybrid energy storage systems. The most important control that the hybrid energy storage systems perform is charge management.
Charge allocation problem is such a problem that we select ES banks from the HIS system and determine the charging current of the ES banks.
Charge migration is the energy transfer from one ES bank to another.
Charge replacement problem is similar to the charge allocation problem, but this time we want to discharge the HIS system to support a load profile.
We implemented HES system from scratch. We designed controller circuits and the power converter circuits, which are embedded in the modules. We assembled the batteries and the associated circuits into a bank module in a 19-inch rack. AC power converter modules are also assembled in a separate module.
Now we are introducing the algorithm to determine the optimal operating conditions of our HIS prototype. We start from an energy profile, which could come from the power supplies or the load devices. The energy profile could be a constant or varying with time. The top-tier algorithm assigns the power to each ES bank, with a global consideration of the bank capacity, rate capacity effect, and self-discharge rate. Having obtained the power assignments, for example, the power of the supercap and power of the battery, we forward this information to the control unit. Then the control unit will determine the optimal CTI voltage and the corresponding charging and discharging currents. This part is the bottom tier level algorithm, and we will talk about later. Note that in these slides, the dashed line denotes the signal flow and the white arrows denote the current flow. Now we describe the bottom tier algorithm part. The bottom tier algorithm, which is implemented in the control unit of the prototype, takes the input from the outcome of the top tier algorithm, namely the power assignments, and another set of the input to the control unit is the open circuit voltage and the state of charge of each ES bank. The control unit takes this input and computes the charging or discharging efficiency at different CTI voltage levels. Since the efficiency of the ES bank are different from each other, we compute the overall efficiency and keep tracking the optimal efficiency point by setting the CTI voltage to the values that corresponding to the optimal efficiency. After we determine the optimal CTI voltage, the charging and discharging current for the ES banks are derived accordingly. The control unit will send the CTI voltage and operating current settings to the charge transfer interconnect and the chargers. And the HIS prototype is operated based on this information.
You can initialize all systems with clicking Initialize button. Current and voltage status of all banks are displayed on each graph. Send button transmits current and voltage values to control each bank. If auto simulation toggle button is on, all system is controlled by an embedded algorithm. Stop button finalizes all system.
The university booth is from Monday to Wednesday near the technical session rooms. Please check the program and visit us there. Thank you.